So here we have a Section B FP2 question. The Section B questions are worth 18 marks in FP2, so that's just a quarter of the paper rather than a half, and they're always on something to do with hyperbolic functions. The first part of the question is only worth 2 marks. What we just need to do here is be careful to do what we've been asked to do, which is to use exponential functions to prove this identity. There are other ways to do it. We could use hyperbolic identities, but we will only get the marks if we use the method we've been asked to. We're then going to show that the derivative of r sin x is this, and also show that r sin x can be written in this log form. Now we've got 9 marks here. To make sure that we pick up all the marks, we'll have to be very precise. In particular, when taking the square root, we need to look at the fact that we have the positive or negative square root, and we've actively chosen just to take the positive square root, and we'll say why we've done that. In part 3 then, we've got to find an integral. Now this integral looks very similar to what we had in part 2, so we should be expecting something of the form with r sin of something, and indeed the answer here does look very similar to this, so that kind of matches up. So we'll be able to use part 2 in order to do part 3. Finally, in the last part of the question, we do need to give an exact logarithmic form in our answer. So we just need to make sure that we do that. We won't have any decimals, we'll be giving it as an exact log. So it'll look presumably something like this. And again, this looks very similar to what we've had in previous parts in the question. This first part of the question should be quite straightforward. So making sure we use exponential functions. We can start with one side of the identity, and in this case we're going to start on the left hand side where we had cos squared u minus sin squared u. Then using the exponential function identities for cos u and sin u, we substitute these in place. It's worth putting brackets to make sure that when we square this, we square everything. Brackets are one of the most common places where mistakes get made, and in particular here, when we expand this squared term and subtract, we'll need to use brackets to make sure that we get the correct values. So multiplying everything out, showing clearly what we've cancelled, we do indeed end up with the value of 1, which was on the right hand side of the identity. So we've shown that this is a true identity. Notice the way it's set out. This is very standard. We start with the left hand side, we do some correct mathematical steps, and we end up with what was on the right hand side. In part 2 of this question, we first need to find the derivative of y equals r sin x. There's a couple of ways to do this, but usually it's going to be easiest to start by taking sin of both sides to get sin y equals x. We could differentiate implicitly, or we could actually just differentiate both sides with respect to y. That would give us cos y is dx dy. Now dy dx that we're after is 1 over dx dy. So we can reciprocate on the other side to give us 1 over cos y is dy dx. Now that is a value for dy dx, or rather an expression for dy dx, but that's in terms of y, and we'd like it to be in terms of x. So we can use the identity. In the formula booklet, we're given that cos squared minus sin squared is 1. We can rearrange that to get cos y on its own, and we get plus or minus the square root of 1 plus sin squared, but sin squared is x squared. So sin squared y is just x squared. So that's plus or minus the square root of 1 plus x squared, which we can put in place of cos y. So when we've done that, we appear to have just about finished, but this is where we need to be careful about this plus minus sign. So if you picture the graph of r sin x, the gradient is always positive, and dy dx gives us the gradient. So because we need the positive gradient, we don't use the plus minus sign, we simply take the positive square root. Remember that if you see a square root sign, that means the positive square root of, just like the power of a half means the positive square root of. If you want to allow for positive or negative roots, that's when you'd have to put in the plus minus sign. So this is our final part of the answer here. We then move on to write y in terms of logs. We start with the same first step to get sin y as x, and then we use the exponential definition for sin y, so a half e to the y minus e to the minus y. I would just multiply everything through by 2 to make the numbers a bit easier. Y have fractions, it's easier to deal with integers. And then also what I've got here is an e to the minus y. If I multiply everything by e to the y, then I won't have this negative power of e here. So what I'll get is e to the minus y times e to the y gives me 1, and then I've got e to the y squared here, and I've got an extra e to the y here. So this is actually just a quadratic in e to the y. So what I will do is just put the e to the y squared term, the e to the y term, and the constant term on one side and equate it to 0. I can solve that in any way I like. I've gone for completing the square, and this leads me to an expression that e to the y is x plus or minus the square root of x squared plus 1. Now to get y on its own, I'm going to log both sides, and here I've got log with a plus or minus. Now what can we do about this plus or minus? Well, if this was minus, because the square root of x squared plus 1 is bigger than x, that would make this a negative value. Now can we have e to the y being equal to a negative value? Well, e to the y is always greater than 0, so no, we can't. So we can only take the positive square root, meaning that our final answer is going to be log of x plus the square root of x squared plus 1. You could also think of this as the fact that we know that logs are not defined for negative x. So again, log of this value, the value would have to be positive. Here we want to find the definite integral. So we've got an integral that looks a lot like the standard integral. I'm just going to rewrite it slightly. So instead of having 4 here, I'm going to have 2 squared, and instead of having 9x squared, I'm going to have an x term, 3x squared. This suggests the substitution u equals 3x. So when I'm integrating by substitution, I need to find du dx. That gives me 3. Now in this integral, I can't see the 3 there, so I'm going to move that 3 over. So when I substitute for dx, I'm going to use a third du. The other thing I need to do is remember to change the limits. The 0 and the 2 are limits in terms of x. I'm going to make this into an integral in terms of u, so I need limits in terms of u. So I just have a look at the substitution u is 3x. So when x is 0, u is 3 times 0, which is 0, and when x is 2, u is 3 times 2, which is 6. So putting this all together, I get my new integral. So what we can see here is where we had a dx before, this has become a third du. I can put constants outside the integral sign if I like, or I could put it inside. I find it easier to work with any constants outside the integral sign. Then everything else has pretty much stayed the same. The u here is replacing the 3x, and the new limits, the 0 and the 6, are replacing the 0 and the 2. Now this is a standard integral, and I can just write that down straight away. So I mustn't forget that I've got this third, and then I've got r sin u over 2. That's a standard thing that we get in the formula book. We get r sin x over a for the integral of 1 over a squared plus x squared, and then I've got my limits. Now I need to show that I substitute those limits in. So first of all I substitute in that u is 6, and then I subtract what I get when I substitute in that u is 0. And then because we're after an exact value, we'll use the log version of this. So r sin of 3, which is 6 over 2, is this expression, and r sin of 0 is 0. So I'll just tidy this up a bit to give my final answer, which is in exact form of a third log 3 plus root 10. Now on to the final part of this question. So we're trying to find another definite integral, and we might notice that what we've got is a function and its derivative, where the function is r sine x and we've got its derivative here. So that would suggest one method would be to do a substitution where u is the function, in this case r sine x. We'll have a look at an alternative method in a moment. So going ahead with this substitution, we differentiate du dx. We've done that in the previous parts. We know that we get this expression here. And having a look at this, I can see that I've got this expression with the 1 over root 1 plus x squared and the dx. So I can just move this dx here and replace all of that with a du. So I'm going to go ahead and do that for that part of the substitution, which just leaves me with the r sine x, which is the u over here. And then finally the limits, I'll just need to sort those out. So when x is 0, u is r sine 0, which is just 0, and when x is 1, we've got that u is r sine 1, and using the logs definition, that ends up being log of 1 plus root 2. I can then substitute everything in place. So we've got the r sine x becomes u, we've got the 1 over root 1 plus x squared dx becomes du, that's this substitution over here, and then we've got the limits. We had 0 and 1, and they've become 0 and natural log of 1 plus root 2. So then we can just go ahead and integrate this. So if you integrate u, you get a half u squared with the new limits. Don't go back to x's. A few people get confused at this point. If you're doing a definite integral, you have gone from an integral that was difficult with a function of x in terms of x, you've turned it into an integral that's easy with a function of u in terms of u, and your limits are in terms of u, so you substitute the u limits into this u function. You don't go back to x's. The only time you might go back to x's is if you had an indefinite integral and your answer would be a function of x. So here we just go ahead and substitute. So we can use the first bit here. When we substitute in, we get a half, and then u squared is a half of log of 1 plus root 2 squared, and then we get a half times 0 for the other part, which is just 0. So our final answer is a half, and then the log of 1 plus root 2 all squared. This cannot be simplified any further, and that's in exact form. Okay, the other method we could use has a bit of a trick to it that's quite useful. Doesn't come up very often on FP2, but it's worth just having a quick look. What you can do is integration by parts, where u is r sine x. You put this into the integration by parts formula, and what you'll get is your u is r sine x, so your v dash is 1 over root 1 plus x squared, so your v is also r sine x, and your u dash is 1 over root 1 plus x squared. So when you put this in, you end up with your uv just being r sine x squared, and then it's minus the integral of u dash v, which is actually the original integral. So what we can do is to say that the integral we're looking for is r sine x squared, evaluated between 0 and 1, minus the integral we're looking for. So if we add the integral we're looking for to both sides, we get that 2 lots of the integral we're looking for is r sine x squared, evaluated between 0 and 1. So to get the integral we're looking for, it's a half of that, and then when we substitute in the values, we get a half log of 1 plus root 2 all squared, the same as before. You might want to pause the video to check that and actually try out the whole parts thing yourself. Some people don't even bother to write out the parts, it just kind of seems obvious. But given that there's a few marks here, you might as well show some working to make it clear what you're doing. The mark schemes here, there's not a lot to take particular note of, but you might want to pause the video and just have a look at exactly where the marks were allocated, and things like, in particular, where you had to make it clear about choosing the positive roots. This is the mark scheme for part 3. Again, you might want to pause the video. And the mark scheme for part 4. Again, you might like to pause the video. I've also put on here the examiner's comments for this question. These are quite interesting and worth taking a read through. This is the end of the video.